We're going to talk today about simplifying radicals. We're going to use this method for anything that is not a perfect square number. And a perfect square number is a number that has a square root. So some typical numbers that we use when we're looking to find the square root of something that isn't a perfect square number would be numbers that are perfect squares. So perfect square numbers are numbers like 4, because the square root of 4 is 2. 9, the square root of 9 is 3. 16, 25, 36, 49, 64, 81, 100, 121, 144, 161, 196, and 225. Those are pretty typical numbers that we would take the square root of and that we should know in our head. We shouldn't have to use our calculator to take the square root of 100. We should already know the square root of 100 is 10. When we simplify radicals that don't have a perfect square number, that are not a perfect square number, so if I simplify something like the square root of 20, I could rewrite the square root of 20 as something that has a square root and something that doesn't. So I could rewrite it as the square root of 4 and the square root of 5. I already know 4 has a square root, which is 2, and then radical 5 would stay as radical 5. We also want to account for the fact that 4 actually has 2 square roots, a positive and a negative. Now in geometry we don't use that a whole lot because in geometry we're usually talking about lengths of sides, and so we would negate the negative anyways. We wouldn't use that. So we would only use the positive. Now you might be wondering, why didn't we do 10 times 2? Well, we didn't in particular we did not pick 10 times 2 because the square root of 20, if I rewrite it as the square root of 2 and the square root of 10, that doesn't help me. I am no closer to being able to simplify it because the square root of 10 doesn't have a square root and neither does the square root of 2. So this isn't helpful. It's not incorrect, it just doesn't help me at all. Now that's just one way we can simplify square roots. We can also simplify square roots with a factor tree. We could take the number 20 and we could do prime factorization on the number 20. So I could make it 2 times 10 and then 2 times 5. Now because I am taking the square root of 20, I'm looking for pairs of 2 of the same number. So there is a pair of 2's. For every pair, I pull 1 out of the radical symbol, and for everything that doesn't have a pair, I leave it inside. So let's try one more. Let's look at a number like the square root of 72. Now 72, if I think back to those perfect square numbers, remember that was 4, 9, 16, 25, 36, 49, 64, 81. What I like to do is I like to take half of the number and look only at anything less than that. So for example, half of 72 is actually 36, so I find it right away. But I would never check any of these numbers because they're not going to go into 72. No way, because I already know half of 72 is 36, so it has to be a number less than half. So I could rewrite this guy as the square root of 36 and the square root of 2. So that would be plus or minus 6 radical 2. Now if you wanted to do it the other way and do a factor tree, we would start with 2 and 36, 2 and 18, 2 and 9, and then 3 and 3. So I'm using prime numbers. Now you may have gotten straight to 2 and 36 and been like, oh, I'm done. I know the square root of 36 is 6, so I'm not going to do the rest of this. If you didn't notice that right away, though, you would pull out your pairs. So I have a pair of 2's that I would pull out, and I have a pair of 3's. Anything I pull out gets multiplied together. Then I have 2 left inside the radical. So that would be the same thing as 6 radical 2.